Well, we've got a lot to get through, so I will try and do this as quickly as I can. So welcome to lecture 3. I hope you enjoyed last week's. This will be following on. Won't be as technical on some bits, so I won't be asking you to do any maths, but there is a lot. So we're going to have a look at tokamaks today. So I don't think anyone needs to do the sign-in form, but if you haven't signed in already, screenshot it, do whatever you need to do. If you've done it before, you don't need to do it. Right. Okay. So here's where we are in the course so far. So we've done our overview. We've done plasma physics. Now we're having a look at tokamaks. This is still subject to change if people don't like what we're covering or we want to cover something else. But this is generally the way we're going to go. So we're on tokamaks today. Today's sort of learning objectives, we're going to have a look at how plasma physics fits into the reactor design. So we follow on from last week. Have a look at the main sort of sections of the tokamak reactor and what they're for. So the breeder blanket, the magnets, and the diverter. We're going to have a brief introduction to some of the material challenges and plasma ignition stuff. And then sort of have a bit of an awareness of other tokamaks around the world, and then especially a bit on jets at the end, because it'll be important for your tour that you're going to do next week. So if this actually works, I should tell you how to sign into this when I click on it. So come on. If not, I'm just going to take questions the old-fashioned way. Right, I give up. Right, okay. Come on. Now it doesn't want to die. No. All right. Okay, so can anyone tell me what a magnetic mirror is if we were listening last week? Anyone? Yeah? Yeah? I'm taking hands up or whatever. You don't. No? Anyone online want to butt in and tell us what a magnetic mirror is? Okay, it's fine. So this is basically what a magnetic mirror is. So it's where we can have charged ions flowing, and generally you can't have them bouncing back because they'll have a negative velocity. And generally, if it's in sort of a linear plane, you'll lose energy from your field of lots of atoms going around. So the solution to that is having it in a big circle or a donut or a tokamak, where you can keep it flowing round and round and round, and you don't really have the issues we talked about last week. So naturally, it gives a tokamak-shaped device, which we're going to cover today. So you can see it's got plasma going around and various different magnets to shape and control that plasma. So, it's not going to work, is it? Right, we'll take hands as well for this one. So I would like you to tell me what's right and what's wrong with this fusion reactor design from Spider-Man 2, including precious tritium, the power of the sun, and the power of my hand. Raise hand or whatever. Just let me know what you think is right with it and what you think isn't right with it. Rob? Correct. He should be absolutely dead as well as everyone else in that room. Any good things about it? It's a fair point. We've got online saying bro's too close to the sun. Correct. And I could give you the benefit of doubt as well online that they could be magnets. My take on it was tritium is precious. It is one of the most valuable materials by mass. Plasma is contained by what looks like magnets, highly inverted commas, and it is the power of the sun. And what's wrong? You can't really control with robot arms, although robots can be involved in fusion reactors. How we get energy out of this, and everyone in the room would be dead. So we're going to have a look at how we can actually address these sort of issues. So we have our deuterium and tritium fuel. We'll put this into our big plasma containment device, for example. We want to extract some energy, and then we'll take out the rest of the unburned fuel and the impurities. What's missing from this this diagram, do you think? Any ideas? No?
Maybe coolant.
Coolant's important, but the main one is we need to get more tritium out. So, because we actually essentially burn our tritium in the plasma and use it up, we need to find a way to keep this reaction going and create more tritium somehow. And then once we do that, we'll take the rest of our unburned fuel, once you've removed the impurities, put it back in, and then we've got a nice little cycle that hopefully will be the sort of dance that defines nuclear fusion. So let's have a look at how we actually do that in a proper reactor. So this is ITER. I'm going to use ITER as my main example for this presentation because it's a big tokamak, but also it's furthest along sort of its development cycle for a lot of these, and images are widely available. So I've just ripped a lot from their website for this. So we have our big tokamak. So firstly, first thing to look at is we've got lots of magnets. We've got essentially three sort of sets of magnets. We've got the solenoid in the middle. We've got colloidal magnets that go around the edges. You can see the blue. And then the toroidal ones are the big V-shaped ones around the side. We need to create some tritium. So we have something called a breeder blanket, which uses lithium-6 to then uses the neutrons from the reaction to then create lithium-6 and split it into tritium and helium, which then can use to fuel the reaction. And then we have our energy extraction and sort of plasma exhaust. So where any impurities in the plasma can be extracted, any low energy bits can also be taken out. This is sort of what it looks like as a CAD model, and you can see the ridiculous size of it with a person per scale. ITER is massive, and there's not really anything like it at the moment. Most of the reactors that you will see are a lot smaller than this. So any idea? Oh, Pete, well, we're just gonna have to ignore this. But any ideas how we should start a plasma reaction? So plasma is incredibly hot, and to actually create like fusion plasma, we have to overcome the interactions on atoms themselves to get them to crash into each other. So it needs to be very, very hot. Any ideas how we might go about starting something like that? How will we get it really hot? No? Come on. You're on the right lines that we can use the magnets. We'll go into it in a little bit. Any other ideas? Beam injection, correct. Someone's done their homework. Microwaves are also used, but more what I've seen is radio waves. But generally, yes, you can put high energy beams in there. It'll excite the atoms, and then you will sort of create plasma. So I've got a little diagram here. So this is just a cut off of a bit of ITER. So first we have to get rid of everything that's in our chamber. So it's a giant vacuum chamber. So we need to get rid of all the air, all the impurities. We just want to be able to have gas in there that we want to fuse. So first we charge up our magnets. These require a huge amount of energy. So we need to actually have a step in there where we basically turn them on and get our plasma confinement ready to go. We need to put our fuel in. So generally it's put in as a gas to start with. So we'll fill it with deuterium and tritium. Then we'll actually use the magnets to create a big electrical current and basically resistive heat the plasma. And that'll get it most of the way there in terms of the temperature that we need to actually start creating fusion power. Next, then we have generally a secondary device that will then basically take the plasma the rest of the way there and heat it up hot enough so things can start actually colliding with each other and creating fusion. And then, boom, once we've got our sort of critical temperature, we have enough energy to overcome the Coulomb barrier, and then we'll release a significant amount of energy. These last two steps are incredibly oversimplified, but that's the general gist. And then to actually sustain the reaction, generally what you'll do is you'll put in pellets of deuterium and tritium, just because it's easier. You don't have to worry about sort of gas flow back and then igniting, so you blow your reactor up. So you generally want pellets because it's not as bad. So there's a few different ways of doing this. So you've got your ohmic heating, so you pass a current through the plasma to create a lot of electrical resistance. You can use neutral beam injection, so you fire neutral atoms, you have them at high kinetic energy, and then they'll collide with the sort of gas, and it'll transfer kinetic energy, and generally, well, that'll heat it up. So it's like someone said, microwaves, so you can do, well, it's similar to this, radio frequency heating, so you're having specific heat frequencies used to excite the particles of hydrogen. Iman wants to come in. And then laser heating, you can also use lasers, just do it. This is essentially how they got the one inertial confinement result where they had a positive plasma output rather than over the energy they put in. Although if you included all the surrounding paraphernalia, it wasn't positive, but generally you can use laser as well. So we've given that a brief coverage. There's so much that can go behind this. All of this is really intense, but we're just giving you like the sort of top level so you can have a look for yourself if you're interested. So this is an example of neutral beam injection that it's actually proposed for ITER and it's getting built. So you can see it's massive. The amount of stuff that you need to accelerate a lot of particles at that energy to start colliding with stuff and then to actually inject it into the tokamak is substantial. I don't know if this this diagram is zoomed in at all, but I imagine it's not. But we know the size of the ITER tokamak, and then this is just one example of like some of the surrounding stuff that goes with it, how big it is. So one of our big three that we're going to talk about, magnets. And don't worry, we are going to cover both magnets and breeder blankets in their own individual lectures. So superconductivity, we need superconductive magnets to actually create the force required. So between 5 and 20 Tesla is a ballpark for a lot of these, allows for our shaping of the plasma. That's an example of one of ITER's 18 magnets, toroidal magnets. You can see how small the people are inside there. It's ridiculous, to the point where some of these magnets have been cracking over their own weight because it's a very brittle material. Generally, the problem with superconductors is you need near absolute zero temperature to operate. So you've got something that's hotter than the sun, and then on the other side of that, you've got something near absolute zero. It's quite an engineering feat. Generally, to improve this, we've got high temperature superconductors are being developed. None of them are sufficient yet, but they're doing better. So we can lower that temperature differential. And then ITER's magnets will generally collectively produce a total magnetic energy of 41 gigajoules. To understand, I don't know if any of you understand how big a Tesla is. It's one of the worst units that exists because 1 Tesla is massive. The Earth's magnetic field is thinking on the order of 0.25 microtesla. So this is pretty strong. It'll definitely fry your phone. But yeah, this is like CERN's magnets are like not as powerful as some of these. That's how much like force we're talking about. So generally, the shape of the plasma, it's not only going around in a circle. We also have the sort of D shape, ends in a little bit of a cross towards the diverter. Generally, we sort of end up pinching it with the toroidal coils. So I don't know if I do have. So this is an example of the actual magnets in all their glory. So you've got your D-shaped, your toroidal ones at the top, and your sort of, cross-shaped ones, the poloidal ones on the bottom, or on the outside. So it generally keeps the plasma away from the wall, so you don't melt your reactor, which would be quite bad, and just gets it in the right shape for you to carry on doing stuff. And generally, lower energy plasma will sort of be directed towards the diverter so it can be extracted and then hopefully put back into surface. So the diverter, we've mentioned it a little bit. This is generally the exhaust of the whole system. So the magnets sort of direct the lower energy plasma over here. So we get rid of our spent fuel. So you'll end up with like a lot of helium in there that you sort of want to get rid of. And then even like the walls of the reactor get eroded over time because of the amount of, or evaporated even. And you don't want that in your plasma, so you want to get it out somehow. Arguably undergoes the highest heat load per unit area of anywhere within a tokamak. So yeah, 10 times higher than a spaceship entering the Earth's atmosphere. It's ridiculous. The amount of heat and energy directed towards a fairly small part is nuts. And generally they won't survive for the entirety of plant operation. So ITER has generally got it as a system of cassettes. So you can have a robot to sort of replace individual ones. Because they just know it can't survive. So they're going to essentially do the maths, figure out, okay, when's this part going to fail, and then replace it before then. So here's a little bit more of a better look at what a cassette sort of looks like. Primarily made from tungsten, so it is the material with the highest melting point, well, the metal with the highest melting point, which is about 3,200 degrees C. And the plasma has the potential to just evaporate that. Which is why you want your confinement to be very good. So this is just an example of a little pipe. So this whole curved surface is made up of lots of pipes. So the temperature has to drop from the surface of the tungsten from orders of like thousands of degrees to about 350 degrees for the copper chrome zirconium tube. If you go higher than that, the copper properties will just sort of dissolve. All the precipitates will just stop working essentially. So that's your maximum temperature the pipe can be at, and that still has to go down to about 150, because if you have steam at above 150 degrees, you generally lose a lot of energy. So this is it's full of cooling pipes just to extract a load of energy as well, and then also remove a lot of the plasma. So you can see there the plasma has an energy, a fusion plasma has energy of like 15 to 50 keV, and 1 EV is about 11,000 degrees C. So if we didn't have good confinement, this would all be just hitting our reactor and melting it. Generally, you will potentially have water in this particular design, but you could use other coolants like helium. Actually, something else to note as well, things expand when they get hot. So you can see on this pipe, the tungsten is actually in sort of slices. That's because if it does expand, it won't actually expand into itself and then crack, because tungsten is incredibly brittle. It's actually quite awful. It's really heavy. If it also evaporates into the plasma, it can do something that's called plasma poisoning, which is generally where if you have an atom that's quite large in your plasma, which is full of tiny atoms, it'll absorb quite a lot of energy and just reduce the sort of efficiency of your reactor. So ideally, you'd use something like beryllium in replace of tungsten, but beryllium's both like really toxic and there's not enough of it. You could potentially use beryllium to build 1.5 ITERs, I think, if you used all the beryllium in the world. But it has an atomic number of 4, and it is one of the best other melting point metals. So this is potentially the most important part of a fusion reactor. So it's the breeder blanket. So it's made to make more tritium. So you use generally lithium-6 and some form of neutron multiplier. Generally, you go for lead. So that means that, well, a neutron multiplier is essentially just an atom where if a neutron hits it, it will then create more neutrons as a result, because they'll fly off. And then with these neutrons will be slow enough to hit the lithium and then undergo fission. Not fission. Well, it's the same fission as if like in a proper fission power plant, but this one doesn't create loads of energy, well, the same magnitude of energy at least. And this will then create tritium and helium, which we can then extract the tritium, then put back into our fuel cycle. This also acts as shielding for critical components. So it's basically absorbing as many neutrons as it can and a lot of heat energy. So this is the majority of the energy extraction. Just covers as much surface area of the tokamak as physically possible. So you've got loads and loads of pipes in there. So for example of how much they're trying to do, ITER's blanket covers an area of around 600 meters squared, aiming to provide, well, over 700 megawatts of thermal power. And ITER's mainly trying to operate on a Q factor of about 10, which is 10 times the energy out than is put in. So that's not bad. So here's an example of what all of it might look like on the bottom. And here's an example of a basic cutaway of what it might look like on the inside. Generally, lithium and lead are required. But the current debate is, do you have it as pellets or do you have it as liquid? So you can just fill these empty holes where it says PBLI in there with pellets of lithium lead. It'll do the job. It'll create tritium and basically trap it as a gas form inside the little pellets. It's not as corrosive and it's quite easy to remove them because they're just balls of the metal, right? The problem is that you're not getting a constant flow of tritium out. So you could use it as a liquid instead. You can then have that flow to another pipe, and then you can extract the tritium that way. The main problem with that is it's one of the most corrosive things that exists. So lithium, likes to react with everything, and liquid lithium lead is worse. It's horrible, but it's really, really good for extracting the tritium. And then you also have a separate channel to then flow in with potentially helium as the coolant, which is where you can extract your energy and turn your turbine. So here's an example of like what a whole power plant might look like. Don't worry about all the numbers, they're quite small. So can you see my mouse? So number 1 is where the tokamak building is. That's where the whole thing that we've been talking about so far will live. Then at number 3 over here, that's where we'll do all of our tritium breeding. Then the assembly hall number 4 is massive. So these parts are so big that they basically have to build them there. So for example, the magnets, superconductive magnets are not superconductive when they're made. You have to heat treat this metal to then make it superconductive. The problem is that a superconductive magnet is generally very brittle, so you can't bend it into the magnet shape you want after you've done that. So that means you make the magnet and heat treat it all at once in a giant furnace, and then you'll assemble the part and put it together. This other big building over here is the power supply for the neutral beam injector, that massive thing we were looking at before. And then you've got a hot cell facility over here. Does anyone have any idea what a hot cell facility is? Well, you might technically see some if you go to Culham, because that's what the MRF sort of does. So a hot cell facility is what you use for dealing with radioactive material. So ITER knows that a lot of the reactor will become radioactive. So you've got to be able to deal with that on site, especially if you're taking bits out like the cassettes. If you're dealing with your liquid lithium, dealing with all that sort of stuff, going to be quite radioactive. So you need to deal with it on site if possible before you then properly decommission it and safely store it. So we've gone through ITER. ITER is a really good example. It's also potentially the biggest. So there's some other examples here. So this is the Globus M2, which is a Russian spherical style tokamak. It is just generally more spherical than a normal tokamak. They're just trying to reduce the size of the central solenoid and make the whole thing smaller. It's smaller, it's cheaper, it's easier to build, that sort of stuff. And then we've got Spark on the right, which is an American one. It's actually a sort of pulsed tokamak style reactor, so it's very close to inertial confinement fusion, which we'll talk about next week. But generally, they're not trying not to have a sustained plasma in the same way tokamak will do, and which just wants to keep running like a furnace. This one has have pulses to get your energy out. So just for a little comparison, I've done this by eye, so it's not entirely accurate, but that's sort of what we're looking at, the difference, which is crazy. Some other spherical ones that are of interest, STEP, which is the UK AEA's one. I'd love to have loads of examples from STEP in here because they do fund my work, but they haven't decided on a lot of stuff yet, so I haven't got any pictures. And then there's also Tokamak Energy, I think, are also doing a spherical one. Generally, it's a preferred option because it's smaller, cheaper. You generally want to make these things, test them to destruction, and then go again, rather than have one big experiment you're just gambling on to work. Any ideas what making it smaller will do, though? Any problems with making it smaller? You can get away with the magnet power isn't generally that much of an issue because there's this thing called Repco tape and similar things. You can generally, it's very, very good, and you can wind it to essentially get as powerful magnets as you want in quite a small area. But the main problem is that it's smaller, so you've got to deal with a very similar heat load in a smaller space. So there's not as much surface area to dissipate that heat. The cooling will be less effective, and also the shielding that you can possibly have is going to be much worse or much thinner. The central solenoid is also much smaller. So if we go back to this one, is quite small compared to ITER's one, which means that it's going to be a struggle to fit everything in. So they have a lot more engineering challenges, but are generally cheaper and are probably the preferred way to go long term. So some other ones to look into. I will make a map of where all these things are and like some stats about them. But generally, Princeton's got a pretty good project. Japan are very on it with their super advanced one. East and West are things you should definitely be aware of if you're into looking at jets, because, well, they're basically the next generation of experiments, so the next generation of jets. And West currently holds the record for longer sustained plasma. Then Demo, which comes after ITER, potentially, which is going to be, I want to say, about twice the size of ITER, which is a concern. But yeah, it's already on the way and they haven't finished ITER. But with how long ITER has taken, I'm glad they've sort of started. But it's basically going to be ITER making power, essentially. It's a demonstration reactor. Commonwealth Fusion Energy are definitely worth looking into. They're very good. And then South Korea, I know less about, but it sounds pretty good. And I was surprised to see India on here as well with their SST-1. I don't hear much about India's sort of fusion projects, but it seems like they've got a good handle on things. So finally, I think this might be the last one of my failures on the surveys. What problems do you see being a major factor over a plant's lifetime? Any ideas? Taking questions in the chat as well, if you fancy it. Come on. Yeah, true. And it's also very difficult because the plant becomes radioactive, so you can't put people in there. Yeah. So parts won't survive for like the whole lifespan. ITER is aware of this. They have basically have, I think, one entire replacement planned for everything over the plant's lifetime. It is also a special case because they're not just going to replace stuff like for like. It's a big experiment. So, for example, their breeder blanket stuff, they have about 4 different versions they want to try out to see which is the best. Any other ideas? Mm-hmm.
Of the plant would grow and have to like change it.
Mm-hmm. So those secondary neutrons aren't as bad for radiation damage, which we will cover separately, as the primary neutrons from the fusion reactors. They just have so much less energy, so they're not going to cause as much damage. So you're right, and but neutrons aren't generally going to corrode things. They'll just happily sit. Yeah, so that's one of the jobs of the breeder blanket is essentially just shield all this stuff from neutrons. So neutrons going anywhere, they shouldn't be as bad. They cause a lot of radiation damage and part degradation, you're right. And yeah, with the thinner one, it's going to be worse. But let's see what I had on here. So yeah, so we've got to sort of so high heat flux, we've got to consider sort of the erosion / evaporation of the surface of your parts. Radiation damage. So as a brief look before we start that in a few weeks, here's an example of a pure tungsten part in what should be a demo spectrum. So this is a simulation of the radioactivity in demo, which comes after ITER. So after 5 years, your pure tungsten part isn't pure tungsten anymore. So you've got to consider not only is your part degrading because of the temperature, because of the radiation, it's also changing composition, which isn't good. Then you've got to consider replacement of these parts, which thankfully is considered and is possible. A massive one is tritium permeation, which we'll probably have a little bit more of a look at later. But so tritium is essentially just hydrogen, right? And things at temperature with hydrogen loves to get inside bits of material. It will just happily just be absorbed, which isn't good, partly because hydrogen will help assist like cracking and failure mechanisms, but also you lose tritium, which we don't want. Some plants have accounted for this in the fact that the hydrogen may flow out to the other side of parts, which you can then collect secondary, but generally it's not good. And then obviously we've got all the standard stuff like corrosion and all that lot, which is why coolant choice is very important, and why they generally will pick helium, or will generally just accept that some corrosion might happen with water because we understand it very well. So right, I think that's my whiz through of tokamaks. Has anyone got any questions before we move on to jets? We're happy to take any questions at all. Or are you okay with sitting on that for a little bit? Yeah. I know it's been quite broad, but it's the choice between go broad or go deep. So I went broad first. Oh,
Why are they building bigger and bigger?
Well, that's not the general trend. So for ITER, they are building bigger, partly because they have almost unlimited money. So the ISS has, ITER has cost on a similar sort of ballpark as the ISS space station, and it's an international collaboration. Bigger generally means it's slightly easier to deal with some of the heat flux. It's also easy to fit a lot of your electronics in. So we've got to control and monitor all this plasma as well. And every time you put a component in to do that, you're taking away wall space from the breeder blanket, which means that your tritium output is lower. So it's easier to do that on a bigger one than it is on a smaller one. But smaller ones are cheaper and they're generally favored by the private sector. And more and more of those sort of companies are popping up. Probably because no one really has the funding to just do a massive one like ITER. But yeah, it's a good point. But I generally say the trend is smaller rather than bigger. You have questions?
What is Demo's estimated?
I want to say, I feel like I read somewhere like 100, but I don't believe that. Let's just say I'll get back to you on that next week. But let's just say it's at least 20. It's because if you double the size of the reactor, actually, well, times in by 4 the volume that you've got. So it's much better. Iman might know in the chat what Demo's Q factor should be, but it'll be bigger, but the whole thing will be bigger. But I don't think they've broken ground yet, and I don't know if it's wise to do that while ITER hasn't even produced any fusion plasma, which is meant to happen. Well, they're meant to get online in 2035. They're meant to produce a DT reaction in 2040, which is also the timeline of a lot of other reactors to get on the grid. Iman doesn't know. I'll look it up afterwards and I'll share it with you. Yeah, it's just going to be bigger. Any other questions? No? Anything burning? Oh, you can always contact me and I'll let you know. Okie dokie. So for your tour that you're going to do, you're going to go to JET, which will be nice, JET in Culham. So it's the Joint European Torus. It is the world's longest running, was the world's longest running fusion experiment and the first in the world to run DT reactions, which is deuterium plasma. Previously held the record for the best Q factor, which was 0.67. So not positive, but it's pretty good. It was the first one to actually use a diverter. So that's a major step because pretty much every reactor now has a diverter. There are some that operate without, but not many. Yeah, most of the design that you'll have seen in like this presentation and for other like reactors was influenced by JET and the experiments done at JET. It's currently being decommissioned. So any idea of why that's, well, it is important. So it's the only one to run so long running tritium. So taking it down, taking it apart safely is a massive, like, important job. And we'll learn a lot doing that. So if we actually get fusion on the grid, we'll actually have to decommission these plants at some point because they don't run forever. And as we've seen, that they degrade. So they definitely won't run forever. And it's not like some fission reactors where they can just go, yeah, it'll last a bit longer. These definitely won't. So taking it apart, understanding where like all the damage is, or the radiation is a really important undertaking. Actually, as a slight side point, so you'll see this image basically anywhere you go when you look at JET. So half of it is with the plasma on and half of it is with it off. You technically can see some of the plasma, but that is the low energy stuff that's actually emitting light. The higher energy stuff you physically can't see. So there is plasma all through that. It's not just on the bottom. That's just the low energy stuff that we can observe. So these are just some more cliff notes. So between 2009 and 2011, it was shut down basically for an ITER rebuild, where they fitted some of the first wall plasma facing components that JET has, and they've upgraded some of it. So you can see there's a lot of beryllium on there. I mentioned why beryllium is not ideal, because we can't actually build reactors out of it long term, but it's still very good. You've got a lot of tungsten and things, tungsten coated with things. You see the diverter on the bottom, essentially in purple and red, and then you've also got your first wall components, basically all in green. And yeah, so in 2021, they had their second run of DT experiments, and they broke the record for sustained fusion energy. So this isn't Q factor. This is the amount of energy they've got out over a period of time. I don't know how long that was, so you'll probably have to ask them when you're there. But they basically got the most energy out of a sustained fusion reaction. And then, the decommissioning is expected to last until about 2040. So just to sort of wrap up, the trip training. Oh, I've missed the bracket there. That's going to annoy me. But yeah, so you're going to have a full day tour of the UKAA campus at Culham. So hopefully you'll be seeing jet and mast, which is, so if jet informed ITER, mast is generally informing STEP and other spherical tokamaks. Hopefully you'll maybe even see the MRF, which is the materials research facility, which is generally where they deal with radioactive material and analyzing it. They've got some cool SEMs where they've retrofitted them because radiation shreds electronics. So they've got all the electronics essentially outside of the SEM. So meet at the engineering building at 20 to 7 on the 29th. Bring some food, it's going to be a long day, and valid photo ID, please. Passport or driver's license is good. Yeah. 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 They don't put these things outside. There's a lot of things which might corrode. Yeah, so just a little summary. So yeah, tokamaks are incredibly complex with a lot of important bits. The ignition is difficult, but you can do it in lots of different ways. Generally, sort of neutral beam injection is currently favored. The magnet systems are very important, and we'll cover them in a separate lecture. But we need it to not melt our reactor and to sustain a consistent fusion plasma. The diverter is a key component. If we can't extract the impurities in our plasma, then our plasma will stop producing energy. And without the breeder blanket, we actually can't use any of these reactors. We will run out of tritium, and that's it. So yeah, ITER, whilst a good example, is not the only way to design a tokamak. Hopefully we'll show you some more designs of other ones. Yeah, so I'll leave you with, well, can contact, I don't know if this QR code works actually, but contact me on WhatsApp or email if you want me to answer some more questions. I will share the slides as well. And I think I'll leave you with our meme of the week, which is about stellarators, because we're going to do accelerators next week. Other reactor designs, so inertial confinement fusion, accelerators, and we'll probably cover some alternative fuel choices like deuterium, and potentially stuff that doesn't even need deuterium or tritium. Yeah, hope you enjoyed it. If you've got any questions, please let me know. The lecture, you don't clap your lecturers. Right, anyone got any questions? Yeah, if you've got a specific question for Culham, over there. If you've got questions for fusion, I'm over here. Yeah.
Why neutral beam injection?
Generally the one that's produced the easiest results, even though it's massive, like undertaking to actually do one of these things. You can generally also have your fuel injected along with it. You can, it's just generally easier than having like loads of lasers, having radio waves. It seems pretty reliable from what I'm aware of it. Yeah, I'm not too up on it, but I can double check, but it's fairly reliable. Any other questions online? No? Well, I'll wait around for about 5-10 minutes if anyone has anything they want to ask. Hello. I will share them at some point, yeah. All of them. Yeah.
In like a
Yeah, we're gonna sort of drop a folder out, yeah. Along with other like stuff to read and bits and pieces.
So if the sign in didn't work, is that fine?
Yeah.
I was curious. Obviously, you mentioned like there's no one way to do things.
Yeah.
Different types, different methods, like your neutral being injected. How much sort of like collaboration, like I guess globally, there is like things like in that fusion, where like, is it like, okay, we're gonna try this type of thing, and you do this, or is it more like, or is it kind of like the space race kind of thing where?
Well, it's a bit of both. So a lot of countries have their own individual projects. So like we've got STEP. We've got like America have their own individual ones. Japan have theirs, whatever. Then you've got things like ESA, which are just genuinely international collaborations. Like Westinghouse was involved with fitting some parts the other week. I don't know, I can't remember where the magnets come from, but like it's a lot of different people interacting. It's basically most of Europe, and then the US. I think China as well, but you'd have to fact check me on China though. But yeah, it depends on the scale. The smaller ones you can generally budget that. Right? You can run that yourself. Then it's also basically a massive science. So you've got a lot of places where people will share some information, all information. But and for example, with my project, which is essentially doing materials testing, like we collaborate a little bit with quite a few people in America who have similar testing rigs. So we share some information. We obviously want to publish our own stuff.
Yeah.
But also at the same time, we want to help them. But because we stop helping other people, then they will stop helping us.
Yeah, exactly.
So
and it's just way to make a breakthrough.
Yeah. Yeah.
To,
Yeah. Generally, I think a smaller company is going to crack it, or somewhere in China. It's international and also not.
cool.
Yeah.
Thanks.
Welcome.
I'm just wondering if are these lectures recorded?
I'm recording it right now.
Okay, cool.
Yeah.
The last one.
Yeah, that one should be up at some point. I'll have to re-record the first one because I forgot to press record halfway until like halfway through. So I'll just re-record that, and hopefully we'll put them all on YouTube.
Oh, okay, great.
Yeah.
Yeah.
Welcome.
Can I just ask, how do you actually put the fuel in?
So
you were saying that like pellets.
yeah.
How do you get them in without-
So there was, I mean, a good thing was posted by UKAA or STEP, one of the two, yesterday. That I think I might have shared in the chat, I might not. But there's a few ways you can just like sort of fire them in. There's like their current design, I think, was like basically look like a fan. Basically, it's loaded and then fling them in. But there's a few different ways you can do it. But yeah, I haven't looked at exactly the mechanism, but I can try and find it for you. But yeah, they're just generally almost fire them in.
Yeah, because my other thing is there any like wall of the reactor that would be better at surviving longer that doesn't like that you don't use it to make more tritium and then just find
Well,
the way to make tritium?
the problem is that there isn't really. You have to basically cover as much of the reactor as physically possible to create more tritium. So anything else is like a luxury. Generally, it's all just coated in tungsten or a tungsten composite or something, tungsten coated with something else, just to help it survive. Because tungsten's quite good at surviving radiation damage. It's got a very high melting point. Just the problem is it's very, very heavy and it's a problem to work with because of this high melting point. And also, it's got a very high atomic number, so it can poison the plasma. Yeah. But it's generally the best you have, what we have. Fusion is just a summary of compromises. I think is the best way to describe it.
If you had like an infinite supply of tritium, is there anything better you could do with the wall?
Oh yeah, you just basically like just make it more, like, just fill it with pipes essentially. You just turn it into pure energy out if you had unlimited tritium. So one way they're trying to get around this tritium problem is have you heard of a CANDU reactor?
No.
So basically that's a fission reactor generally in Canada, but they use heavy water. So that is something that will then create tritium on its own by just accident. And that tritium they collect can then potentially be used to kickstart a fusion reactor. But it's not on the scale of you could just replace all the breeder blanket.
Yeah. That's what I was thinking. Is there any way you could just use a different source of tritium that's not the reactor
Well,
fuel?
Well, we'll cover it a little bit next week, but there are alternative fuels that you can use. So like deuterium on its own, or you can even use, I think it's boron and protons can do it as well. But they require a lot more energy to start.
Yeah. But there's always a trade.
Yeah, there's the summary of it. So sorry guys, you've got your hands up. Sorry. I haven't got my. I don't know if I can put my speaker on. Oh, I must disconnect from the. Hopefully, hopefully then you'll be able to. I'll be able to hear what you have to say. I can't hear anything.
I don't think we're speaking, that's why.
If
Sorry.
not, I don't know what my laptop's doing. Can you just text, put your answers in the chat, please? Jamie Edwards, what's the hardest part of all of it to do? Emo, I think he's gone now. I don't know which one he was referring to, but the hardest bit, all of it, getting the whole thing to survive, dealing with the radiation damage is very difficult. And since we haven't technically proven breeder blankets yet, I'd say that's the most important part to get right, which is why ITER has a few different setups for it. Hi, William. I don't know if I'll be able to hear you, so if you can type your message in the chat, please. Read a blanket by Liberty, which is us. Yeah, shock pellet injection, Iman suggested as an answer to your question. Generally, just fire it in any way you can, like, without any sort of backblast.
Yeah, that's what I was wondering.
well-
Get it in without stuff coming out.
Well, think of it this way as well. You can't really have any components that can be affected by magnets. It's not good. It has to be simple and reliable. It's one of the problems with ICF because they basically work on firing pellets in and imploding them, like almost like a car engine. They go like every once or twice every minute, and then you have to just deal with that. So if it fails, your reaction stops. William, I can't hear you, so you've got your hand up. I don't know if you have any questions.
The pellets for their fusion, they actually use the input of pellets as part of the heating process.
Right, I think that's everyone online happy or left. So otherwise, I'll thank you for watching and I'll see you next week. Later.